Hello everyone. I'll be giving an introduction to computer vision. We will go through some image transformations, example programs using OpenCV, get an overview of edges and shapes, and see these working using OpenCV. And we'll also see what computer vision has to offer more, cover an overview of where the research is moving. Okay, so what is computer vision basically? Humans use their eyes as sensory input to see the world around us as an image or a video. This image is then processed in our brain, aka the interpreting device, which results in interpretations of these images. For instance, looking at this image, I see green, I see grass, I see trees, and I see bridge over a spring of water, and so on. Now, this is human vision. What is computer vision? A camera is the source of sensing an image when we talk about computer vision, and the interpreting device here is replaced by the computer itself, where the program does the interpreting and ideally should result in the same interpretations as humans. So, this is what we see an image when we look at it. However, this is what a computer sees, these numbers here. So, computer vision is the field of study which aims to bridge the gap between what we see and what a computer sees. So, let's look at this representation of an image, what a computer sees. For a computer, an image contains discrete number of pixels and can be represented as a 2D array of numbers. A 2D array of numbers where each element is a pixel ranging in grayscale. These ranges from 0 to 255. 0 being black and 255 being white. A color image, on the other hand, contains three such 2D arrays. Now there are different color spaces. One of them is RGB, red, green, and blue. And then there are several others like HSV, LAB, and so on. The resolution of an image is given by the number of rows cross columns. For example, we say this image is of 360 cross 420 and so on. Now, there are different image formats that you see on your phone or on your computer, a JPEG, a PNG, a TIFF, a GIF, etc. And several such images in sequence, when they are clubbed together, they form a video. We can also consider an image as a function f. A function f of x and y, which gives the intensity at a position x comma y. Here the image as a function is defined over a rectangle with a finite range with a domain a, b cross c comma d and has a range from 0 to 255 as we discussed in the previous slide. Now given an image, or as we just discussed, representing an image as a function, we could modify this function, or in other words, we could modify an image by passing it through a system S and generating a modified version of this function called G. Now let's talk about what could we do. So this system S could be different kind of image operations or filters, and one could change the original image into a grayscale image and perform several operations like image segmentation, like brightness or contrast changes, as we see in our day-to-day lives in our phones when we try to use some app to change the brightness or contrast. So let's look into the details of what goes behind the scenes when you're trying to just move a trackbar and change the brightness or contrast and many more. So to be able to see these working, we are going to use OpenCV. OpenCV is an open source library which was created by Intel and allows us to build algorithms using the different tools and functions which are contained in OpenCV. It is open source, it is free, You can easily install it, and I highly recommend following the official documentation here and following the steps to install it. Regardless of you're using Linux or Windows, you can follow the steps, which are very, very descriptive with pictures and everything, and you could use this. Okay, so let's talk about how segmentation works. So this is a very basic kind of segmentation that I'm trying to show here. So given an original image, this is a very famous image of Lena, known for its different image properties in the history of computer vision. Now we can use OpenCV's library to convert an RGB image, which has three color channels, red, green, and blue, to a grayscale image, which is plain one channel, single channel, ranging from 0 to 255, as we discussed. So if I perform an image operation on this grayscale image, where if the pixel value is greater than some threshold, I make it white and I leave the remaining pixels value as it is. So this is a simple thresholding process, and it gives this kind of a segmentation effect. Now let's look at this working with a Visual Studio project. So this is my Visual Studio setup of the OpenCV using Microsoft Visual Studio, and I have followed the steps as given in the link below from OpenCV official documentation. And I include all the libraries that I need from OpenCV. And I include the standard IO stream and corresponding namespace for C++ programming. So let's discuss primarily about OpenCV related code here. So as you know that we will have to read the image from the disk. So say this is my project folder, the root folder, where I have stored the image, which is of Lena. And if you can see, and I open this, this is the image. This is fine. And then mat is a constructor. Basically, it's a container rather, which allows to hold the variable image or the 2D representation. And the good thing here is that if you hover over mat, you can see what this class provides. And as you can see, it provides an n-dimensional dense numerical single channel or a multi-channel array. In our case, it's a two-dimensional array. And it is three channel because it has a RGB color space. And then using imread, we just read the file Lena into the variable called image, which is of type mat. And we check if this has valid data. And if it doesn't, we throw an error. And if it does, we just want to use another function called named window, which will create a window to use that can be used as a placeholder for this image. Now you will notice that there are two versions of this. I have commented out one on purpose, and I'm showing right now that we're using the flag window auto size. So I create a placeholder where I want to hold this image, and then I display it using that. So now let's try to build this program. So this is a basic load and display program for an image. So once my build succeeds, I will go ahead and run this. And as you can see, I'm able to display the image in this placeholder called display window. Okay, if you cannot see this is the name of the placeholder called display window. So now let's come to the point, what is window auto size? So this flag here does not allow us to resize this image, and the function named window automatically adjusts the size of the image according to the image size and does not allow the user to play with it. So then this wait key 0 here, it waits for a keystroke in the window, and the minute I press a keystroke like now, it will close the placeholder. So let's try this with with the variation of the same function. So I'm going to change this, rebuild it, and then once the build process is over, I am ready to run this program again, and I see the image being displayed. But now you can see that, which allows me to resize this display window as I like it. Okay, so this was a very simple, like a hello world program in the world of computer vision, where you could just simply load an image using IMRead and then you could display it. So I'm going to press a keystroke, which is going to close this, and then we're going to go back to our um, image transformation. So this was for loading and displaying. Now I'm going to comment this out, and then let's go to another program here, which I have ready for you to demonstrate image segmentation. So let's look at this first. So apart from the basic and standard includes and using namespace, I read a file, I check if the input is valid, then I want to create another container or a variable called gray image where I'm going to change its color from RGB to gray. This is very basic and standard, and you can read more about it or how to do it or what does it exactly do inside it in the documentation of CV. And after this CVT color, I get my grayscale image here. So, and I'm going to display using the same method, original images, then the grayscale images, and then here is where I perform that simple thresholding that I talk about. So I loop through all the rows and all the columns, and at each pixel value, like we just discussed, you can consider this image as a function f. So you just check if the function f at x comma y is greater than a specific threshold. You could make it completely white, and that's what I'm doing here. And I leave the remaining, I don't have an else, so I leave the remaining as it is. And this particular image will now have a segmented image, and I will display that over here as gray image after segmentation. And I even this is a new function for you. We can save an image once it has been created or it has been modified in whatever name you want to save it. It gets automatically saved in the same folder where you're working, and IMWrite is used to save this image with this syntax. And if you hover over it, you can see specific details of IMWrite on here. This function writes, saves the image to the specified file, and if you want to save it to a specific location, you can give the entire absolute path here, and so on. So I'm going to build this program to visualize how we get uh, this kind of an output. And once the build is succeeded, so you can see this is my, you can see these are the outputs I get. This is my original image. Then there is a window called gray image, which is on my other screen. I'm just going to drag it here. And this is the one which is for image after segmentation. And all of them were window normal. So I'm able to play with their sizes. And you can see that you are able to perform transformation if you consider this image as a function of the location x comma y, and you can see that at particular location, at every location you loop through each row and each column. That is basically all the locations, all the positions of this two-dimensional array. And if you check for these values, if they are greater than 100, you make them completely white. So all these values which you see here, super white, that is 255, which you specifically modified. So this was a simple image segmentation. Okay, now moving on. Similarly, if you consider your original image, convert it into grayscale, and then add some scalar to each and every pixel at this value, you can achieve a brightness, a brighter image. Okay. So let's see how we can do this. So I'm gonna comment this code. So the reason I'm doing this again and again is primarily so that I don't have more than one main. So you can only have one main function inside of a project. So because I have written the code not in a modular or a function base, I've written the entire separate use cases. And also, most of these are from the samples of OpenCV. So once you will install OpenCV, you will see a sample folder which will allow you to use these as it is, and you will be able to see them by just changing the image names and the location, and that'll be a good start for any beginner. That's how I got started at the first place, and that's why I've chosen the basic stuff to for us to be easy to and understand what's going on. Okay, so you load an image, okay? You read image and you create a new image of the same size where you want to put your output. And what you do is you basically want to loop through all the image rows and columns again. And you want to add some scalar over here to improve the brightness, okay? So for a minute, just forget about this alpha because I'm going to ignore this and consider this is 1. So all I'm doing is that image at that location at every channel, all RGB and all three of them, add some scalar to it, and then see the brightness change. Okay, so I'm going to keep alpha. So the program is going to ask me to enter the alpha value, the beta value. I'm going to keep alpha as 1. So all you're doing basically is the image plus some scalar. So let's build this program. And then let's run this. So this is the um, initial output. And as you can see, it is going through a basic linear transforms like here in the code. And it asks me for an alpha value. I'm going to give this as 1. Ask me for a beta value. So I'm going to give a value of like say 50. So you will notice that this was my original image. And sadly, this is we cannot change this because we have not specified. Okay, never mind. So this was our original image, and this is the new image. So you realize that as you add a constant, you are moving the value at each pixel. You're basically modifying the intensity at each pixel location by like plus 50. So in the scale of 0 to 255 here, you are making all the pixels more towards white, that is 255. So this was with 50. Now let's run this again and then let's play with this to see, to get the intuition behind this. So now maybe I want to make it more bright and I'm going to go with 80. So this is my original image and this is what I see in the modified image. So this clearly gives us a good idea of what's going on. You are modifying every pixel to be increased more towards the brighter side. Okay. Now getting back to where we were, now we could also, as you saw in the code, the same operation in a different way is used to change the contrast by multiplying the original image after changing to grayscale with certain amount of constant. Okay, so you can multiply that, you can scale that up and get a contrast. So let's have a quick peek how we can do this. So the same code, the very same code where we are looping through each row and column and multiplying this, let's keep beta as 0. So we don't want to do anything with the brightness. So I'm going to keep alpha as like say twice and beta as 0. So you can clearly see here that the original image was this, but I have been able to change the contrast of the pixels in this image to a different contrast, right? And we can tweak this around and see. So keeping the alpha value as maybe 2.5, I want to play with the contrast more and I want to keep beta as 0 for now. So I will see a drastic change in contrast here as compared to this one. So let's say we want to keep it as alpha value to be 1.5, and then we want to give no change the brightness, only the contrast. So we see this again. It's a less of a contrast change, but it's still there. Okay, great. So moving on, we saw we saw segmentation, brightness, and contrast changes brought about by simple pixel level image operations that you performed, and you can very well replicate this following the tutorial on OpenCV, like I mentioned before, and you will see these are very basic pixel modifications that we are doing, but you can see more math behind this and more detailed um, image operations that you can perform to achieve blurring, erosion, dilation, or something called as Sobel, etc. So, how do computers make sense of an image? So, this is how we modified images. Now, computers have to extract meaningful information from these images. So the way they work, or the way computer vision has worked from the basics, is that we try to extract basic features. We try to write programs to extract basic features from an image, such as edges, colors, or corners, or blobs, or the magnitude of the gradients. That's a new term, and you might think that why would we do that, and what exactly is that? We'll come back to that. And then orientation. Now, building upon these basic features, then computer vision comes up with uh, methods or more complex features. These are nothing but features, are also known as image features. So we come across with people or faces or cars. These are like features at a higher level or a higher dimensionality. How does a computer make sense of these features to conclude what are objects? Then how does a computer make sense of an image features and objects to conclude what region are we talking about, like grass, water, road, or sky? So these are the different levels at which we will be looking at, or these are the different levels at which computer vision looks at this whole problem of image understanding. So let's talk about edges. So an edge is a place of a rapid change in the image intensity function. So if you see this original image, it has a very drastic edge here, and these are white, but this has a drastic edge over here with a different color. And with a human eye, you can clearly make out that this is an edge. If I ask you to draw an edge, you know this is an edge. But for a computer, how does a computer make sense of this and knows what is an edge? So for a computer, the pixels where the intensity undergoes significant amount of change, or a drastic or a sudden change, is known as an edge. So if you see intensity function along the horizontal scan line along this, then you see it was smooth. It was consistent across this. It was all white. Probably this was all 255. And then once we came across the black, when we are transitioning from white to black, this rapidly dropped over here, and across black along this line, horizontal scan line, it's again consistent, and because it might be zero, but you see a drastic change here again when you transition from black to white, because this is an edge. You're undergoing an edge. And once we take a derivative of this, we see that if edges correspond to the extrema of these derivatives, the first derivative of these images gives us edges. So this is how computer vision enables a computer to recognize what edges are, by taking derivatives. And this is nothing but one of the gradients. So if you have an image of Lena and you perform this operation where you're trying to find the gradients and edges, and thus edges, you will get something like an edge being detected like this. But it's not that straightforward. We undergo a lot of steps. So one of the very famous edge detectors was, or is, canny edge detector. So what it does is it smoothens the input image by a Gaussian mask. So what we do is that we smoothen it and then we calculate the horizontal gradient g of x and g of y at each pixel location by convolving with different Gaussian mask or with gradient mass. Then we compute the gradient magnitude and direction at each pixel location. Then we apply something known as non-maximal suppression, which what it does is up until here, the image that you get at this point in the process will have many such edges. Now we have to thin these edges and come to specific bold edges with a much more confidence that these are proper edges, and that's when we do something called as non-maximal suppression. You don't have to worry about it. You can. This is something not relevant for you right now, but the point here is that we this is what an edge detector can do, and this is what computer vision can do. So then you compute high and low thresholds based on the gradient magnitude for the entire image. And after performing a hysteresis thresholding and morphological thinning, we come up with an edge map which looks something like this. And if you find this entire process very interesting, and we should to be able to move further in depth, you should definitely go through in detail how does this work, which is a canny edge detector. So let's look at to get you started, you can always look at a demo using the sample programs, and I will show you something from there that how can you use the inbuilt canny edge detector from the OpenCV library to detect edges in your image. So this is my program. I am reading an image, that same Lena image, and I create a new image variable to store of the same size and type to store my new final resultant image. Now I change the source image, this image to grayscale image, and I will blur this image to smoothen it like we discussed, and this smoothing is performed mainly to remove noise. In most of the processes in computer vision or algorithms, we do this as a pre-processing step where smoothing allows you to get rid of a lot of noise, and it forces pixels different to their neighbors to look more like their neighbors, so it kind of smoothens something very noisy. And then you perform a canny. So in this is an inbuilt function, and if you just hover over it, it tells you everything that it takes as an input and finds edges in the input image, marks them in the output map edges using the largest value to find initial segment of strong edges. So whatever you're getting from here is not the best you can do. You can do better than this. There have been various variants of Canny to further improve it. So it takes the input as an 8-bit input image, okay, and it takes the final edge map where it has to store it, and threshold 1 is for hysteresis procedure, and the second threshold is for hysteresis procedure again. And the aperture size is nothing but the kernel size, which I have here. So let's run this. So what you will see here is I have the original image and I have the edge detected image. So this is what Canny can do. It can give you exact edges where you look at. So edges are very important in general. So suppose you want to detect a line and you're making a line follower. You could detect edges because the line will be clearly marked with a white line in the entire background of a gray, which is a road background. You can work with edges. Then people use edge detection and in different reasons for detecting cracks in the road. Uh, then they use such kind of a detector to use to find defects in chips. So there are various places where edge detectors are used. So let's talk about shapes. So now that we have detected edges, can we detect shapes? So using contours with OpenCV, you can get a sequence of points or vertices. of each white. So white patches are considered as polygons in this particular example that we are talking about. So suppose you'll use something called contour finding. So all you need to know is contours in this whole black. Where do I get contours? So you will get points basically of the different vertices of such shapes. And if you're able to get those points, then you will have to use some kind of a logic whether these are 3 points or if there are three vertices, if that makes it a triangle, and if the contours gives us something like five vertices, if it's a pentagon, and so on. So you can identify features whether it's convex, concave, equilateral, and etc. by calculating and comparing the distance between these vertices, and you can do a lot. So let's look at how we can do shapes. So let's look at what we do to detect different shapes. So what we exactly do is I have this image that you saw uh, loaded in finding contours.png. Now I create a grayscale image from here, RGB to gray function. Then we threshold this grayscale image to get better results. So because in our case it's a black and white image, we use a binary threshold over here, and we store the points or the vertices we get in the contours in our variable pointer to contours. And then we use the CV function called find contours, which retrieves the outer and optionally inner boundaries of white or non-zero connected contours in the black background. So this is typically meant for a black and white image where it will be able to do this. Now we iterate through each contour and we obtain a sequence of points of contour pointed by the variable counter. And you will see that what they're doing here is basically they see if there are three vertices in the counter or four vertices in the counter, and based on that, they draw lines to be able to show you that this is the triangle that is detected. So there are four points being detected, which for us means that okay, it could be a quadrilateral. There are seven detections, then it could be a heptagon, and so on. So these are open source. Like I mentioned before, all of these are open source codes that I have uh, built, and I'm trying to use this for demo purposes. And if you see this, then this was your raw image, and this is the tracked image, and we can see that it has detected these. So all the four vertices ones, so the one, two, three, four are square or a diamond, are marked with the same, like they have the same color, indicating that they both had 4 point vertices when fine contours was run on them. Similarly, a triangle of different angles and different viewpoints is blue. So this is pretty cool that we can track shapes using this method. Now, what will be interesting to do on top of this is, are you able to only track a circle which is red in color? So you could use this technique and also use an AND condition for tracking the color alone. So you could use that you only want the values of red color. And how will you do color tracking? So you will have to merge something like a shape and a color tracker to only track the red triangles, for instance. Okay, so let's close this. Let's go back to our slide. And then, so this was all about the demonstrations, or very basic, very trivial stuff from the computer vision side, but a very good starting point for you to get started with different tasks that you are thinking about deploying on the robots. Now, a lot more is possible using computer vision concepts. So, for instance, detecting faces in any image is very robust nowadays. So you wonder how Facebook shows you tag suggestions on any face in a photo, and then you should definitely check out the original paper of Viola Jones, which performed very well and had achieved groundbreaking results on detecting faces. And you can see a sample here. All the faces are detected perfectly. And this is one thing which you could also get started with using OpenCV HAR Cascade detector sample code base, and you can work on top of it for more and thorough understanding. So, advanced concepts in computer vision involve teaching the computer different patterns. So, for instance, this is the Afghan girl who went really famous because of the photograph being clicked by a National Geographic photographer, and many of you might already be aware of this. So, um, her identity was confirmed by a professor and a scientist, John Dogman, using iris recognition. So, what is iris recognition? So things like iris recognition or fingerprint matching, you may wonder how you're able to open your phone, how your iPhone or your Android phone is able to detect your fingerprint to be able to allow you to log into your computer or phone. So there is a subfield or a whole field in itself with computer vision, which is pattern recognition, where you can teach the computer there are patterns and they can identify and they can learn and classify, okay, this pattern here of this iris belongs to uh, this girl here, or this fingerprint here, or these specific patterns on a finger belongs to this person here. So vision is also being used for various solving various robotics problems, as you might be aware of. Working with robots, computer vision can help robots navigate in uncertain environments. So, like NASA's Mars Spirit rover has been taking great pictures from Mars, and it helps us study about extraterrestrial life or explore the space more where humans can't go. So if you're able to make the computer vision, if you're able to provide vision to this robot in unconstrained environments where humans can't go, so this will help us like advance a lot in science, and a lot of progress has already been made in this space exploration and in this direction using computer vision. Then a lot of research is going on at Stanford for improving and advancing personal robots. You see ROS base. ROS is a robot operating system. A ROS base personal robot of Willow Garage over here, if I'm not mistaken. Yeah, that's what it looks like. Um, to help elderly, assist people, and to enable robots and humans to coexist together and be able to help us as we are moving more and more to automation and assisted robotics. So, moving towards machines, um, moving towards making machines understand a complete scene. So, if you remember, the initial goal which I mentioned of computer vision is to be able to bridge this gap between what we see and what a computer sees. And researchers have worked a lot and progressed a lot in this direction. And what you see here is a picture from one of the papers which studied context in object detection. So, well, maybe the computer can detect this very well or this very well, but it's not able to detect everything in context. It has to get the context that okay, this is a person and this is sitting on top of a horse, and this horse is also being pet by another person here. So people are working towards more thorough understanding, because when you see an image, when humans see an image, we are able to get not just objects in isolation, not just colors or shapes, but we are able to figure out a lot more. And human vision is just brilliantly perfect, and that's the challenge. So we want a computer to understand images similar to humans, for which the computer should be able to tell, like, these are children, these are the walls, well, these are children, these are one, two, three, four, five children sitting on a dining table or a classroom table. It probably seems like it's their snack break. Oh, they're eating these food, and so on. So the challenge here is to segment and parse an image into different image regions associated with semantic categories such as the sky, the road, the table, the chair, the wall, the classroom, or even identify, oh, this whole scene is of a classroom. So, like we have seen just now that how intensive a process it is to we are starting from something as basic as edges. So can you just one can only imagine that what it must take to be reaching to a phase where okay the computer is able to tell everything apart, okay this is this and so on. So this is a sample from a scene segmentation demo from MIT CSAIL lab, and they have been doing some awesome work on semantic understanding of scenes, because if we have to make computers compatible to our vision, we need them to understand this at that level. So if you visit the demo page, which we will in like just another 2 minutes, you'll see something like this. So how cool is that? Because you feed this image to the computer as you saw. You perform, suppose we saw a one image operation of an if then else, you perform some much sophisticated version of that. It's not going to be anywhere closer to an image operation. And you get something like it is able to tell you, it is able to segment the scene and tell you which region of the image are what. Like bright pink here is the table, or the green images here are the plates, and pretty close to where the plates are. And it's able to do a fairly decent job at segmenting the scene at a semantical level where it's able to tell you. So let's just have a look of this demo and let's see what it does. So this is the scene segmentation demo. It parses the given image into semantic regions. And this is a network. Let's consider it as a black box, which has been trained on some data set. And so let me just give you a very, very high level understanding of what this means. So, um, so like we have seen so many samples that we know, okay, this is grass. So this is something similar. This community of computer vision works on releasing and collecting several data sets, or here in particular of scene parsing, with regards to scene parsing, and it will train the system or this black box. Okay, this is grass, this is maybe water, and it will show several and thousands and millions of images of water and grass to make it understand or learn that this is grass and this is water. So this is basically what they mean by here. Yeah, I just put it in very fancy words. Okay. So the details about the model. Okay. Okay. So let's just take, say, this image, which I showed you in the slides, and then you see that segmentation works very well, if not perfect, and it gives us exact amount. It gives us objects and their pixel ratios. So there were some m number of rows and n number of columns, so m cross n pixels, out of which, okay, this percentage is of table, this percentage is of wall, and so on. So this is a way of like, this is just a metric or a way of evaluating. So they would have something like a ground truth measure. Now, what is the ground truth? A ground truth is what the uh, a ground truth is basically a true or a known measure of a certain quantity. So in this case, objects and their pixel ratios, which when this data set was collected, we already knew what this is, and this is what the machine or the black box is telling us. So we would just compare this with that ground truth, or so-called the true actual value of it should be, but this is what it is, to see how well we have been able to train our machines. I hope it makes sense to you. And then they have something called a spot prediction, where they're concentrating on humans, I think, like how much is their torso or how much is their head, and so on. So let's try a different image. Let's try this. So, well, so let's do an exercise and think what regions can you think as a human. I think the car, the person, this could be a wall, this could be the ground, That's all I can think of. Okay. So, wall, awesome. A car, awesome. A person, great. And the floor, great. So, we got these correct. It could tell you the ceiling. It does tell us the signboard. Oh, wow, awesome. I didn't think of the signboard as it will be able to tell it separately. It did tell the signboard. The door, okay, it marks this as a door, great. Window pane, okay. And light, yeah, that is quite impressive. Yeah, that's great. Let's look at this one. Okay, so this one here tells us very specific things like an ottoman and a sofa, a ceiling, a cushion, etc. Great. So this was just to give you a gist of where things are moving and to encourage you to have a look at this demo maybe and go through stuff which big leaders in this field are doing. Here are some of the resource clips. I will add more to it. So that was about it. Thank you.